Hi everyone, I'm Sarah Lawless, and welcome to my virtual UGIC presentation on the visualization of time-sensitive data. Now, this isn't data that has a due date or an expiration date, but it is data that changes with time. Just a little bit about me and where I work. I graduated from BYU with a degree in GIS a couple years ago and did an internship with the State Division of Emergency Management. From there, I went to MAG, and I've been their GIS analyst for 2 years. MAG is the Metropolitan Planning Organization, or AOG for the area, and we service Summit, Utah, and Wasatch counties. Some of the projects that you'll recognize that we've contributed to are the Front Runner and the UVX bus route. We've also funded a number of trails like the Utah Lake Trail and the Murdoch Canal Trail. We also cover senior services and community and economic development. So if you have any more questions about MAG services, please visit our website, mountainland.org. At MAG, we use a land use model, otherwise called REM, or the real estate market model, to help us project future employment and population data. REM starts with a base year of the most up-to-date, accurate data that we have, and using certain algorithms and variables like tax parcel data, census data, utility data, and land use densities, REM goes into a cycle of building, redeveloping, and populating an area until that area reaches its almost maximum population and employment density. REM currently projects population and employment up to the year 2060, but with most projections, the further away you get from reality in time, the less accurate those projections are going to be. But at least it can give us an idea of what the future could look like in terms of employment and population in this area. This is what REM's data looks like. Here, I've filtered REM's data to represent just the values for Utah County, but originally REM covers the entire Wasatch Front. But just for this demo, we'll just use Utah County's data. There are about 200,000 points here, and each point represents a tax parcel with a building on it. Here, each point represents that theoretical building, like a single or multifamily home or an office or retail building. And depending on the type of building on that tax parcel, there are a certain number of people or number of jobs within that building. So while you've been looking at this data, you'll notice that there's some areas that have buildings that don't exist in reality. So these are clearly simulated by REM. And one of the most obvious examples of this is Eagle Mountain. There's a lot of land out here for a lot of growth, so it makes sense that REM would build something out there. So let's look at the attribute table for these buildings. Here are the 3 fields that I want to be focusing on. For each building or point, there is a year built or simulated by REM, a number for the population, and a number for employment. If the building is a single-family home, it won't have any job numbers associated with it. And the same thing with an office building. There won't be a population associated with it. The year built goes from 1855 all the way to 2060, and anything built after 2015 has been simulated. The rest of it is historical data. We're currently working on updating our base year to 2019 in preparation for the next cycle of projections, but in this demo, I'm using our previous cycle data, so 2015 is the base year. Let's look at the data in 2D really quick to help us identify the patterns, the kinds of patterns that we should be looking for. Here's the population data represented by both Jenks Natural Breaks and Quantile. And the patterns that I notice are primarily that Vineyard, Eagle Mountain, and Saratoga Springs are getting the majority of population growth and the largest number of people, especially in those new growth areas that REM is simulating. Let's take a look at the employment. There's a little bit more of an obvious pattern here. As you can tell, it's pretty obvious that the job growth happens along major transportation corridors like I-15 and state streets. And it also corresponds to retail, office, and industrial zoning in most areas. A lot of this is kind of what we expect to happen, but it's interesting to see it on a map. So these are just 2D patterns though, so let's try and visualize the possible 3D time-induced patterns, the change over that time. I'd like to share some ways that have helped me visualize the patterns that I see over time, particularly in animation, and by using 3D space-time cubes. I'll be using REMS data from 1980 to 2060 because that's where a lot of the visual growth will happen, along with all the simulated growth. So let's just create a simple animation to show the spatial growth of the buildings over time. Here's the same data, but symbolized by year built. The black points are the buildings built before 1980, and everything else was built afterwards. So the first thing I'm going to do before I start animating is create a time date field using the Convert Time Field tool. The input time field is going to be year built, and the output time format is just by year, because that's the format it's in. And then I'm going to name it year built TD for time date. And run it. As you can see in the attribute table, there's a year built TD field. And the default is just January 1st, but it represents the entire year. Next, I'm going to go to the properties of the layer and make sure that it's time enabled. So you go to Properties, Time, make sure that each feature has a single time field, and the time field is that new time date field we made. Between 1980 and 2060, that's what we want, and everything else is good. So you would do OK. Nothing much changed except now that you've got a sweet time slider on the top of your map view. And as you move the sliders for the start and end time, you'll notice that it filters your data to match those time periods because your data is time enabled. Okay, let's go to the Time tab. Here it has your start time and your end time. That reflects where your start time and end time sliders are. And the span is 80 years. You can also lock the start time, the span, or the end time. Let me show you what that does. So let's lock the span. The span is 80 years, so that's not going to change much, but let's change the span to 10 years. As you can see, the time slider has changed to represent that time span of 10 years. So now I can see the 10-year growth from 2010 to 2020. The same thing goes for the end time. We're going to move the end time to 2060, and then we're going to lock the end time. And now all we can move is the start time. So let's check out 2020 on. Obviously that looks like a lot of the simulated data, which is, it's all a simulated data. But what we want to do for this particular demo is we want to lock the start time because we want to see the progress ahead in time. So what I've done is it's using the time span, so that's why it's going every 10 years, why it's locking to every 10 years. Same thing with the time snapping to the decades. And it's for all visible time-enabled data, which I only have one layer that's visible, that's time-enabled. Let's add the animation now. Go to the View tab, click on Add Animation, and now you'll see an animation timeline pop up. Now we want to add each of those decades of data that this timeline can filter out. And I don't want to have to add each keyframe one by one. So what you do is you go Import Time Slider Steps, and it will import a keyframe for each of those decades. So let's just look at the first decade. Obviously it's just got the 1980 data, and then the last decade, which has the 2060 data. At this point, you can render it. First, I'm going to change the duration of it because I think 30 seconds is a little too slow. So I'm going to change it to 15 seconds. And I'm going to render it at 5 frames per second because the map isn't actually moving, so you don't need a lot of frames per second to represent 10 images. let's play the video. Well, there you go. There's your simple time series animation. If you want to add a title or some dynamic text, just select the keyframes that you want for the duration of the overlay. And then select the overlay that you want, like a title or an image, or, for this one, we would probably do map time because it matches the time slider steps. I prefer to do this in my own video editing software because I have more control over the style, but I just wanted to show you that there's the option. This kind of animation can be very useful if you want to share on a website or blog the change of an area over time. Based on how you symbolize the data, you can find some really cool spatiotemporal patterns. Now that we've gone over a basic time series animation, let's move to 3D time cubes. If you're new to Spacetime Cubes, I recommend watching some tutorials online or reading the documentation on them before venturing any further, because they can become quite complicated depending on your data. But if you're brave, and I haven't absolutely bored you to death, let's continue. This is what a Spacetime Cube looks like. Each little cube is called a bin, and each horizontal group of bins is called a slice, and each vertical group of bins is called a series. Each series has an XY location, and each slice is a designated period of time. In other words, each bin represents a spatiotemporal location containing a value for your data. Simple as that, right? For reals though, let's do it in ArcGIS Pro and see what it actually looks like. I'll use the same data that we used to make the animations with the same time frame from 1980 to 2060, but I'll just focus on Lehigh this time. Lehigh's got a booming job market up at Silicon Slopes and has an established downtown district, so it would be interesting to see how REM continues to project jobs in this area. Now, I'd like to aggregate these points up to our traffic analysis zone. The traffic analysis zones are the basic geographic unit that we use in our travel demand model. The first thing that we're going to do is we're going to create a space-time cube by aggregating points. The input features will be our points. The time field will be that special date field we created earlier. For our time step interval, we need at least 10, so I'm going to do every 5 years. With the start time as our time step alignment, because I want it to start at 1980. And then our aggregation shape type will be defined locations as our TAS. And then our summary fields will be for jobs, and we just want the sum of the jobs. And I'm going to fill my empty bins with zeros because I want to know if there are no jobs in that area or if it's an error in my data. In other words, I want to see exactly what REM did. Great. As you can see, there wasn't a new layer added. That's because the space-time cube actually hasn't been visualized. So we're going to use the Visualize Space-Time Cube in 3D tool to visualize it. Great, now it's been visualized, right? This isn't exactly the point. We need to be visualizing it in a 3D scene. So we're going to convert this map into a 3D scene. We need to make sure that our 3D time cubes, their elevation is relative to the ground, so they show on top of the elevation. That doesn't look very exciting, so we'll symbolize it. And I'm going to use Quantile as my method because it helps me see the obvious differences a little bit better. And then I'm going to use a green to red color scheme. Okay, that still doesn't look too exciting from the top, but once you swivel around to actually enjoy the 3D view, you realize that, we're seeing a lot of things. That's a lot of data, but just by looking at it, you can see some clusters of areas with lots of jobs, especially micron and obviously silicone slopes, which is just what we expected. And as you can see, REM continues to project lots of job growth in this area, even past 2015. Let's time enable this so we can visualize it a little bit better. From 1980 to 2060, we're good. We've got that awesome time slider. I'm going to take it down to 2015. Kind of see what things look like. Let me symbolize this a little bit better too. I like to zoom out a little bit so it looks a little bit like a heat map. I just think that's so cool. Okay, and let's see kind of what REM did. Start with at least 2017. We can go year by year if we want, but obviously that's not going to work because we're going by 5-year increments. There we go. So now we're just visualizing one box at a time. So it's one 5-year increment from 2030 to 2035. So here I'm going to lock that time span because I just want to keep going by 5 years. And I'm going to use time snapping to the years. So now we're going 2030 to 2035. Obviously it's picking up that 2025 to 2030 year. That's fine. So there's the first year of simulated data. We can keep going. See things change. I think that's pretty cool. If you look here in 2040, that's going to be 2040 to 2045, we get some job growth right along I-15 that doesn't stay into the next 5 years. Okay, so now that we've done that, let's turn this into an animation just like the one that we did before. I'm going to keep my 5-year span increment locked. The step interval is 5 years, and I'm going to use the time span, so that looks good to me. And then we insert the animation, and we import the time slider steps. That looks about right to me. Now, like I said before, you can add a title and you can add a little indicator that tells you what year you're looking at, but let's render this and see what it looks like. Great, and now we will play the video. As you can see, if you had a little time indicator to tell you what time span it was looking at, this would be really valuable, so you could identify specific time frames where there's a lot of growth. Other than looking like a retro dance floor, this is pretty useful in visualizing simply some relatively complex 3D data. But if you want to do actual analysis on these 3D space-time cubes, instead of animating the visual changes, you can use the emerging hotspot analysis tool. This really helps you see the entirety of the changes over the time frame. I'm going to go back to my 2D map view and run the tool on the original, not the visualized time cube file. So you go to emerging hotspot analysis and input that original time cube file. The analysis variable is going to be jobs because I want to know where the job hotspots are. And I'm going to use k nearest neighbors as my conceptualization of spatial relationships. This is just like normal k nearest neighbors. It includes the cells surrounding the cell that's being analyzed, except it includes a time step up and below in time as part of the analysis, which I think is really cool because it includes the time variable of the whole thing. So I'm going to use 3 time steps. That might seem like a lot, but I think the trends that REM's creating happen over a couple decades. And run the tool. Now this is fairly in your face. As you can see, this area is a consecutive hotspot and a sporadic hotspot. In my mind, that translates to hotspot. And let's check out what areas that is. Interesting that we've got this residential area. That could be an error in my data, or it could be something that REM is seeing that I'm not. But it's primarily Lehigh on the east side of the freeway. And that would be worth looking into. And that's it. Obviously, there's a whole world of visualizing time-sensitive data, and I've only scratched the surface. But hopefully it's inspired some of you to consider looking at your data in a different way, and at least something I shared will be valuable to you. If you have any questions about anything I presented, feel free to connect with me via LinkedIn or shoot me an email at slawless@mountainland.org. Thanks to all those who took the time to watch, and I hope you enjoy the rest of your virtual UJIT conference.